Welcome to the Consulting Specifying Engineer Webcast, Critical Power, Generators, and Generator System Design. This 60-minute webcast is sponsored by ASCO. I'm your moderator, Jack Smith, and I'm happy to join you today on behalf of Consulting Specifying Engineer and Pure Power. Our speakers today are Robert Jones, Jr. and James Ferris. I'll introduce them shortly, but first I'd like to explain the user interface for the webcast system so you can make the most of today's event. Then we'll take a quick break for a word from our sponsor, ASCO, after which you'll hear from today's speakers. Consulting Specifying Engineer uses a very robust webcast platform, so please take note of the following as you're participating in today's event. First, make sure your pop-up blocker is turned off. This is an option in your browser software. If you're having technical problems with audio or the slide presentation, click on the question mark at the top right-hand corner of your screen to bring up a list of system checks to make before escalating to an online technician. If you're experiencing issues with your slides or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of this webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you need a technician, type a message into the Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions area on the left-hand side of your screen. You can use the Ask a Question box on the left side of your screen to type questions for the speakers during the presentation for the Q&A session at the end. If you are on Twitter, you can tweet your questions to us during the webcast by using hashtag #CSEGenerators. You may ask questions at any time during the presentation, and we'll get to as many as time allows. Questions for today's presenters will be answered verbally during the Q&A session at the end of the webcast. To download the presentation slides, use Event Resources on the left-hand side of your screen. To learn more about our sponsor, use the Event Sponsor tab at the top of your screen or click their logo at the bottom of your screen to be redirected to their website. To take the Learning Unit exam and to download your AIA CES Learning Unit certificate, use the Learning Unit Exam tab option at the top of your screen. This webcast is being recorded, including the Q&A session. We'll post the archive on the Consulting Specifying Engineer website in a few days, and we'll send you an email message with a link connecting directly to the presentation after it's ready. For those of you who are interested in receiving a Learning Unit credit for this event, you need to pass a 10-question exam. Take the Learning Unit exam, and to download your AIA CES Learning Unit certificate, use the Learning Unit Exam tab option at the top of your screen. You can complete the exam after the webcast. However, the link will break when the webcast signs off. It will be reactivated on the Consulting Specifying Engineer website with the on-demand version. To receive Learning Unit credit, you must get 8 of the 10 questions correct. You will be notified immediately if you pass the exam, and you can retake it if necessary. After passing the exam, you will be able to obtain a PDF of the completion certificate online by following the instructions provided. In keeping with the American Institute of Architects' continuing education policy, please take a few moments to read the quality assurance slide. Great. Thank you. Now we will hear from the sponsor of today's webcast, ASCO. At the conclusion of the video, you may experience a few seconds of silence because attendees use a variety of internet browsers to view this webcast. speed of the video plays may vary. We'll resume the webcast after the video ends for all attendees.
It's your worst nightmare.
I think we have a problem with power distribution.
The split-second decisions you make will mean the difference between business as usual or a potentially catastrophic power outage. Making the right decisions requires the power to know the details to solve the problem. You need the ability to monitor and control complex power distribution systems with precision and accuracy to be able to check the condition, status, and operation of your equipment at a moment's notice, second by second, 24/7. You need PowerQuest, a critical power management system from ASCO. PowerQuest monitors all of your system components, providing alarms as well as control capabilities on-site or remotely. Please reach us any of the following ways to learn more about PowerQuest.
Thank you, ASCO, for supporting today's program. Please take a moment to review the learning objectives for today's presentation. We will touch on each of these topics. Now, please take a moment to remind yourself about dealing with technical issues during the presentation. I'm happy to introduce today's distinguished speakers. Rob Jones is a senior project engineer at JBA Consulting Engineers with more than 10 years of design experience. He works primarily with medium and low voltage distribution systems, emergency standby power systems, renewable energy design and implementation, circuit analysis calculations, and equipment-based planning. Jim Ferris is an electrical project engineer with TLC Engineering for Architecture and specializes in power distribution for healthcare facilities. Jim has presented at a variety of consulting specifying engineer webcasts, and we're happy to have this expert speaker back with us again. Thank you both very much for joining us today. Rob Jones will speak first, and let's get started.
Hello. All right. There are many codes and standards that apply to generator system design. Today we'll explore some of the NFPA codes and standards and the IBC to identify many of the important requirements and how they could be applied. One of the more prevalent codes enforced by AHJs is the IBC. Chapter 27 deals with electrical requirements, including when and how generators should be considered. There's NFPA 110, which contains criteria for generators used for emergency and standby power systems. There's NFPA 101, also enforced by many AHJs, and contains specific references to the type of backup power required in different applications. Finally, we'll look at NFPA 70. Article 445 addresses requirements for generator installation, and Articles 700, 701, and 702 cover how generators and the associated distribution can be applied to system design of both code-required and optional backup power. IBC Chapter 27, Electrical, really doesn't go into too much detail in itself, but contains references to other chapters and sections where emergency and standby power systems must be provided. Section 2702.1 specifically references NFPA 110, and that emergency and standby systems required by that code must conform to it. Section 2702.2 goes into the references to other sections such as egress and exiting, group occupancies, and high-rises. NFPA 110 makes use of two important terms throughout the standard, EPS and EPSS. I have the definitions from NFPA 110 up on the screen for you to read. But the EPS is basically the generator or generators in parallel and includes up to the first disconnecting device. The EPSS includes the EPS and all distribution equipment and controls up to the load or output terminals of the transfer switches. Here we have a simple generator system diagram. The generator and the disconnecting device is located on the generator, make up the EPS. The EPSS includes all parts of the EPS plus the generator distribution board. The emergency and legally required transfer switches are, and although not indicated here, all controls and wiring between the transfer switches and the generator control panel. Notice I did not include the optional standby transfer switch in the EPSS. The criteria applies to the emergency life safety and standby systems as required by code. There is no requirement to ensure the optional standby systems will operate and perform to the level of the code-required systems. And then here I'm noting the load terminals on the transfer switches. EPSSs are classified using 3 performance and reliability gauges. Class is defined by the minimum time the generator system needs to operate continuously without refueling. Type dictates the maximum time allowed to pass before loads must be re-energized. And the level provides criteria for installation, performance, and maintenance, as well as testing requirements. NFPA 110 Chapter 4.2 defines the system class in hours. Since NFPA 110 is only the standard that sets up the criteria, the relevant class value is identified by the applicable code, application, or AHJ. For example, a battery-based system would require a minimum runtime of 1.5 hours per NEC Article 712A. The class would be 1.5 in this case. NEC Article 712B2 requires a generator to have enough fuel to operate for 2 hours minimum, which would make this a Class 2 system. NFPA 20, which addresses the installation requirements for fire pumps, calls for a minimum fuel supply for 8 hours of continuous runtime. And another example is inpatient healthcare facilities that are accredited through JCO, or the Joint Commission on Accreditation of Healthcare Organizations, need to have a minimum of 24-hour fuel supply per the AIA guideline for design of construction healthcare facilities. This could be more than 24 hours based on the jurisdiction, but the minimum in the guideline is 24. Chapter 4.3 defines the system type in seconds. This is the maximum time allowed by the applicable code to start up, synchronize, and transfer or pick up the load. Emergency systems under NEC 700 are required to be energized within 10 seconds. The type would be 10 in this case. NFPA 20 for fire pumps also requires no more than 10 seconds. And the last example, code-required or legally required standby systems under NEC Article 701 are allowed up to 60 seconds to be energized. Chapter 4.4 in NFPA 110 provides 2 levels for installation, performance, and maintenance of the system. A Level 1 system is required when failure of the EPSS could result in loss of human life or serious injury. Some systems that would fall under this level are NEC 700 emergency systems and NEC Article 517 healthcare essential electrical systems. Some NEC Article 701 systems must comply with Level 1 standards if defined as such. For example, NFPA 101 Section 714.7.1 requires Level 1 standby power for elevators addressed by that section. A Level 2 system is required when failure is less critical to human life and safety. Depending on other applicable codes, NEC Article 701 systems would generally fall under this level. A good way to look at this is that systems used to safely evacuate occupants from the building would be Level 1. Other systems where loss would negatively affect rescue or firefighting would be considered Level 2. Let's see. This slide identifies some common EPSS systems defined by NFPA 101. The type, class, and level are identified in the noted sections. So if we look at the last one, per NFPA 101, Section 11.8.5, legally required standby power provided for high-rise buildings also have 60 seconds to energize the loads, run for 1 hour, and adhere to the level 1 criteria. Although this code only requires 1 hour of runtime, this does not preclude the NEC requirement for 2 hours minimum for the generators. Let's see, NEC Article 445 covers the installation of generators and other requirements. 445.13 provides ampacity requirements for the conductors between the generator up to the first overcurrent device. When the generator is provided with an onboard circuit breaker, the conductors are part of the factory wiring. But if the circuit breaker is located remotely, the conductors must be sized for at least 115% of the generator nameplate rating. All generators require a means to disconnect from the load supplied. 445.18 requires disconnects lockable in the open position. Alternatively, the e-stop can serve this function as long as the generator is not configured in parallel with other generators. Where Article 445 provides requirements for generators, Articles 700, 701, and 702 provide requirements for the use of generators. An EPS that serves an Article 700 emergency system is required to have the capacity to supply all connected loads simultaneously from the emergency system. The EPS is allowed to also serve non-emergency systems, but will require load pickup and shedding ability for the other systems, unless the EPS has the capacity to supply all connected loads from all systems. Article 701, legally required standby systems are required to have an EPS with the capacity to serve all loads intended to operate simultaneously. And since Article 702 optional standby systems are not code required, there are no EPS capacity requirements. All three systems are required to have transfer switches. Emergency transfer switches must be automatic and serve only emergency loads. Legally required standby transfer switches must also be automatic but are not required to be dedicated. Optional standby transfer switches may be manual or automatic. Here we're looking at the same generator backup system from earlier. I have highlighted the separate vertical switchboard section for the emergency system. This is required to comply with NEC 710B, which requires wiring to be installed in separate raceways and enclosures. The legally required and optional standby automatic transfer switches require control wiring back to the generator control panel for selective load pickup and shedding to ensure that the generator capacity is there for the emergency system per code. Here we'll look at a few examples of how some codes define the types of loads that are connected to the emergency and legally required systems. As mentioned earlier, IBC 2702.2 defines the type of power, emergency, or standby for several key loads that are important to the safe evacuation of building occupants as well as those that aid in rescue efforts. Here I've listed some loads that are required to be connected to the emergency system and the relevant code sections. You can take a look at those. Below that are loads required to be provided with standby power. Since these loads are specifically required to be connected to standby power in codes enforced by your AHJ, these would be legally required. When determining what loads to connect to each system, it is important to consider the project location and any local adopted codes. Many AHJs opt to amend codes prior to adoption. An excellent example of this is in Southern Nevada. AHJs in this area have amended the first paragraph of NEC 700.1, which identifies the scope of emergency systems article. They added verbiage identifying specific loads that may be connected to the emergency system. Many of these loads are considered legally required standby in other regions, such as smoke evac systems, elevators and high-rises, lighting and power and fire command center, and HVAC systems that serve emergency and electrical rooms, as well as elevator machine rooms. And now I'll turn it over to Jim to continue.
Thanks a lot, Rob. So now that we've got a backbone for the code basis and done our research, we're going to start talking about how to design an EPS system, an EPSS. So the first step is going to be, obviously, you're going to need to figure out your load. That's really the backbone and starting point of how big your system has to be. It'll help you determine whether or not you're going to be going with a single generator or multiple generators. It's also important to determine what the load is by the different systems that Rob was talking about, which is the legally required, and the emergency, and also the alternate non-required loads. Second step, you're going to start to think about, in my location, how long will I have to run for? I do a lot of work in Florida where we have a huge risk of hurricanes, where a lot of facilities I do work at may have to run as long as 7 days without the grid being available. So it's an important consideration that their generators need to be capable of doing that. If the system is a emergency system, whether or not it's going to be used for a utility peak shaving program, and that would be like a generator demand response program, that's certainly a consideration up front that you need to consider, because it will affect what kind of generators you're using and will affect your installation. Step 4 would be you got to figure out what sources of fuel are available and where your site is. Depending on where your site is, you may end up on a well field where you can't necessarily use diesel, so you may have to go to a propane source or something of that nature. Sometimes that does certainly affect the system. And then finally, you're going to figure out what accessories are necessary. So generators are sized on a couple basic blocks. You're going to talk about the running kVA, which is basically what is your operating load. You're going to talk about the starting kVA. And then, so if I have a big chiller that's going to start up, whether or not it's a cross-the-line starter or a VFD that's going to slowly ramp up the load, certainly makes a difference on my generator, whether or not it can handle that starting kVA. There are some other considerations for it, where like high harmonic content can affect your generator size. Intermittent starting can affect your generator size. Obviously, standard stuff like altitude and where you are in the world can certainly affect your generator size. Just a little reminder that the NEC has a nice little rule for existing installations. We're required we can measure an existing installation for 30 days continuous and then use 125% of that number to figure out what the existing load is on a building. And this could be applied to the size of your generators where you're doing in an existing installation. So when we're talking about how long the generator is going to run for, and not only how long, but at what load that generator is going to run for, we start to think about what kind of rating my generators are going to be. Are they standby, are they prime, or are they continuous power? Basically, the engines are relatively the same, but basically a prime at a certain level would be a standby at a certain level and a continuous at a certain level. So, and I'll show you an example in a second to kind of say that. But basically, a standby would be it's on demand, but you're not considering to run that at full peak load for a continuous period of time. So if you are going to be a load shed site, you may consider going to prime or continuous. This is kind of what happens is, we're looking at a situation here where we've got a generator cut sheet. It's the same generator, the same build, but a 2000 kW standby generator is actually rated 1825 prime, which is actually also 1600 kW continuous. So as I extend the full load runtime, I cut my capacity of the generator. So, what does this have to do with your warranty? You have specific language written into your warranty for peak load and a certain amount of time. So if you're planning on running it at that rate, then you need to make sure you plan for that. And it certainly does take size. So we talked a little bit about Tier 4, about utility peak shaving programs. And right now there's a plethora of literature on the internet. I know Consulting Specifying has a couple of webcasts on it, on generators and the EPA demand. EPA currently has a rule that says if you're using your generators as an emergency system and like a hospital function, they would not be required to be Tier 4. But if you're using your generators and participating in a profit-making generator demand response, then you have to have Tier 4 generators. Tier 4 would basically mean that you're treating your exhaust emissions and putting out clean exhaust. And it does add cost and does add space to your room. And now back to you, Rob.
Thanks, Jim. All right. Okay, so when designing your generator system, there are several options depending on the project size and needs. Small facilities where the emergency loads such as egress lighting and exit signs can be addressed with fully automatic unit equipment, and fire alarm systems addressed with localized batteries may opt to install a quick connection unit for a portable generator for extended outages only. Permanently installed stationary standby generators have a few options for fuel sources. Diesel fuel oil being the most prevalent. There's liquid propane and natural gas are also options. A dual fuel or bi-fuel system allows the generator to operate on a blend of diesel fuel and either liquid propane or natural gas. When considering the fuel source, it is important to keep in mind NEC 712 B2 and 3, which requires the fuel supply to be located on the premise and prohibits the generator to be solely dependent on a public utility gas system. There is an exception where, at the AHJ's discretion, and there's a low probability of loss of both power and public utility gas, where this could be allowed, but it's not very typical. And I think I jumped. If you're looking to utilize natural gas as a way to increase your runtime, but minimize your on-site fuel requirements, a dual fuel generator may fit the bill. Typically, a retrofit kit from a third-party manufacturer is field installed on a diesel generator. The kit is essentially a fumigation system where gas is mixed with the intake air and the diesel performs the spark ignition. This can significantly reduce the diesel consumption, typically getting a 40-60 split. Most generator manufacturer representatives can recommend a dual fuel kit manufacturer with experience on their generators. It is important to still maintain enough on-site diesel to maintain the minimum runtime for the code-required systems and shed the optional loads upon loss of the public utility gas. If you do have a large diesel oil storage system on site, steps should be taken to minimize the possibility of spoilage. Diesel fuel will foul when stored untreated for more than 3 to 6 months. Either the fuel will need to be pumped out and replaced on a certain interval or treated with additives. A fuel polisher system is a convenient way to remove water and contamination from the stored fuel. NFPA 110 contains criteria for the location of the EPS, whether you choose to locate it indoors or outdoors. There are several reasons to consider one location over the other, but it is generally less expensive to locate the generators outdoors. Some project sites may not have available space on the site, so an indoor location may be desired. One of the major items to consider when locating a generator indoors is the intake and exhaust requirements. This normally requires the room to be located at an exterior wall. If this is not possible, a remote radiator or heat exchanger is an option, but adds quite a bit of additional complexity to the installation. NFPA 110.721 requires the space to be dedicated to the EPS and have a 2-hour fire resistance rating. Other EPSS equipment, such as the generator distribution and transfer switches, may also be located in the dedicated EPS room. If the EPS is located outdoors, NFPA 110 requires an enclosure that provides protection from the elements. The standard allows other EPSS equipment to be located in the enclosure, but this is typically limited to a couple of 1 or 2 circuit breakers, and all the other equipment is located indoors due to space constraints. Sometimes you may consider installing more than one generator to address emergency and standby loads. It could simply be due to the peak loading of your EPS exceeding available standard ratings of individual generators, or the project may have requirements for additional resiliency in the design should a generator fail. One thing to consider when selecting your generator rating is the loading at both peak and low times. If you anticipate this to vary greatly, you may run the risk of underloading the generator. Over time, this could cause serious performance issues and damage the generator. Generally, you do not want to load the generator to any lower than 30% of the nameplate rating. So if, for example, the full capacity required for a phased build-out of a new property is being installed up front, choosing multiple generators will allow the system to operate more efficiently by shutting down some generators if the load does not demand the full aggregate capacity of generation. Redundancy in the EPS can be very common for facilities where there's an elevated demand to ensure critical systems are not subject to lengthy interruptions due to loss of utility. In some cases, this could be to protect loss of life, such as life support systems in hospitals, and in others to protect against financial loss in a data center or any other large hospitality resort, etc. In an N+1 configuration, the total required capacity is spread over one or more generators, plus one additional generator is installed equal to the rating of the other individual generators. Should one generator fail, the remaining generators will pick up the full load. Sometimes on very large projects where the generation capacity is quite large, you may have the opportunity to provide some degree of redundancy by breaking down the optional standby into multiple priorities. Sophisticated paralleling switchgear can provide real-time demand load management. The PSG would be programmed to ensure the EPS is available to the highest priority loads, emergency, and legally required standby, and optional standby loads considered critical to the client. The EPS would be sized for these based on connected loads. Additional capacity found during operation due to the actual load demand may allow a fourth priority to pick up less critical optional standby loads, but shed them during peak loads for the first three priorities. The generator ratings should be coordinated with the primary distribution voltage for the property. Below I've listed some common distribution voltages, and the maximum generator rating I would typically recommend based on not exceeding a 4,000 amp distribution bus. If the required capacity is any larger, I'd recommend either breaking up the EPS into multiple systems or stepping up the EPSS distribution voltage to reduce costs. Medium voltage distribution may be considered for generator systems intended to support a campus or large hospitality resort, and step down to utilization voltage where appropriate. Items to consider while designing the generator system are ancillary equipment that supports the operation of the generator. A standard package generator will normally require connections from the EPSS to power the jacket water heater, battery charger, and fuel system controls. The jacket water heater ensures the generator maintains a minimum coolant temperature to ensure a 10-second startup and sync. The battery charger maintains a fully charged starter battery. Other items to consider depending on the type of generator installed may be remote coolant systems if the EPS is installed indoors and adequate ventilation is not achievable. These require power tapped at the generator prior to the EPSS per NFPA 110.7674, and often include an aftercooler water pump and radiator fan. Other things to look at are motorized dampers and remote bulk storage fuel supply pumps, and they're required to be powered from the highest priority EPSS or from the EPS. All right, at this point I'll turn it back to Jim to talk about installation and commissioning.
Okay, so as professionals designing and selecting this equipment, our responsibilities don't end with just at the specification. We need to make sure that it performs how we expect it to, and that comes down to commissioning. So you have to look at the EPS as a system. There's a lot of different components, and then there's a piece that all works together and ties together. So these are a couple of different things that we're going to run through as part of the commissioning effort. Identify a couple of key points that you're going to need to look at if you do get an opportunity to commission a EPS system. The first one's pretty simple. It's the generators. Everyone is aware there's going to be a load bank test for generators. You may have sound testing. You may have emissions testing. You may have to review accessories, like, for example, the jacket water heater is actually required to go off when the generator reaches a certain temperature. In NFPA, it's just something you need to double check that occurs. Load banks are obviously one of the first things that you're going to need to get. The code, NFPA 110, requires that you do a reactive load bank test. I actually inverted these on the slide now that I'm looking at it. The first one is reactive load bank test, which is going to be a 0.8 power factor. And typically that's done at the factory. However, you can do it in the field. I've had a couple of times where it just didn't get done at the factory, and we ended up pulling out a reactive load bank to the job site and testing it in the site. Now, if you do a reactive load bank inside the factory, then you are allowed to do a resistive load bank in the field. And resistive load bank would be at unity power factor 1.0. And that's pretty much that. Load bank test would be, typical load bank test is 2 hours at full load, 5-minute cool down, and then you're gonna hit it with a full block of load of the generator rating. And you need to take a capture of that response and oil pressure and all the readings. typically you're going to run it again for another 2 hours, and you're going to take recordings every 15 minutes throughout the whole duration of all 4 hours and 5 minutes of this. Now, there are other options. You can ask for a longer load bank test. I have done projects where maybe clients wanted to ask for a load bank test, but then even tie it to load shedding to make sure that it works, the system works appropriately, and whatnot. So, sound testing might be, you're in a certain area that has a requirement where you need to have a certain sound level at the property line. A lot of times the generators they're not front and center in the property. They try to put them on the back, and we need to be mindful of that. Air performance is certainly an important feature. Emissions, I've seen generator systems where the emission is too close to an intake, and it's actually pulling the exhaust fumes back into the building because the air that the radiators need is so much. And then, of course, I mentioned a couple of the accessories earlier. Next step is alarm annunciation. NFPA 110 has a huge list of code-required alarms that are required to be displayed first at the unit controller, so on the generator, and then also at a remote location. It is written around a single generator installation. It's not written around a parallel system, so there are some alarms that are good practice that are related to parallel systems that are not necessarily in the list. And then there's a couple of items in the list that aren't necessarily applicable to every system, like I think it's an air start, air shutdown damper. So basically this list, if it says RA, there'll be an alarm that has to enunciate at an intended location within the building. Most of these alarms can be simulated from the generator or the parallel switchgear. And you can maybe do a jumper, or the generator manufacturer can be out there to simulate certain alarms out there in the field. And you need to do it sequentially, go through them all, and make sure that they enunciate at that 24-hour location. As part of the system, we also need to look at the fuel. The fuel is obviously keeps the system running. It's a very important feature. We need to make sure each day tank is going to call for the fuel, and that the level float switches and the way the system is designed to run actually works. We also want to verify that if there's a main tank, that the low fuel alarm will set off an alarm in the building and in the generator switchgear to let everyone know that they need to reorder fuel. So typical low fuel settings would be, like if it's a class 48, you're going to have 48 hours of fuel. And at 48 hours of fuel left, you have to alarm the 24-hour location to let them know reorder fuel. The one little quirk here, which I like to point out, is that typically your tanks, your fuel tanks, there's a piece at the bottom of the fuel tank that is unusable fuel because of the way the fuel tanks are set up. You can never, ever pump that fuel out. So your low fuel alarm actually has to be 48 hours of the gen runtime plus the unusable fuel. So you have to include that because it doesn't count. So just a little quirk to keep in mind. Okay, parallel systems. Parallel systems can get extremely complicated, and the load shedding and generator demand response, they operate and they go on and off depending upon load, what the operating load of the system is. Maybe they'll go off depending on, they'll turn off a generator depending on whether or not, you have 6 generators and maybe only need 4 running. They might shut off a generator. So it's pretty in-depth and pretty complicated. So first one is load shed. Load shed basically would be if I have a system where I've got my critical life safety equipment branches, and then I've got another branch that serves maybe an MRI or maybe a group of elevators. I would actually and then maybe I have a final branch that serves just normal power throughout the building. If I have an engine failure, or if my load is reaching such a peak state that I'm pushing the limits of my engines, I might want to shed off the normal branch and then sequentially go back. So then, after I shed off the normal branch, if I'm still not working, I might want to shed off. In this case, I probably shed off the MRI. And then if I keep going, elevators, and then go back till I have nothing but legally required and emergency system loads running. So usually the amount of steps in load shedding relate to the amount of generators that you have. So if you had a 6-generator system, you might have 6 steps. If you have a 2-generator system, it would only be 2. This is kind of an example of a system that has 2 generators. And you can see that we've got the critical branch. This is a hospital that is in Florida. And we've got the critical branch, which has got a load on it, and fire pump, life safety. Those are all necessary loads. The equipment 2 branch in this case was a smoke control system, which is required to be on in 60 seconds, and it's required to be on, so it's part of our priority 100. That means that you cannot shed that load as part of this layout. We have X-ray, some chillers, and some air handlers, and then we have the normal system. And as you can see, what we do is we're looking at it in 2 different ways in this scenario. We're looking at the priority 100 load, which is the load that has to be on in 10 seconds. And that load needs to be less than however many engines you can get on in 10 seconds. Most manufacturers would say they can get 1 engine on in 10 seconds. Some manufacturers will say something else. But it would have to be tied to the quantity of engines you can get on in 10 seconds. And then priority 200 would be anything I can get on after that 10 seconds. And basically what we would do in this situation is, now knowing the loads of each system, we'd want to commission it and test it. So what you have the capabilities of doing in most of the parallel switch gears and most of the generator controls is simulating a load. And it might be through a PLC, or it might be through a milliamp, like a milliamp generator that they can tie into the terminals of a PLC. And you can simulate loads. I wouldn't suggest that anybody hook up a load bank that's going to overload a system to test it. That certainly would be dangerous. But you can simulate it through the PLC logic by basically simulating a load. So in this situation, I just cut out a snippet of a commissioning document that I've used in order to check the performance of the system. So like scenario 1, basically I just killed power to the normal, make sure that the priority 1 loads come on in 10 seconds, and boom. So they're good. We checked that. So then I've got 2 generators running. I'm going to kill the 2nd generator, and let's just pretend it failed. What happens to the system? And depending on the programming of different manufacturers, they all do it slightly different. They all do have there's some common ground, but there is certainly drastic differences between the manufacturers. They would respond. So like if the 2nd generator comes off, I might shed the 2nd tier of loads. This, just for an example, this actually is a 2-generator system that I'm showing you here. The 3rd scenario, which I tested, was, let's say I have 105% of my loads over 2 generators, but I have 2 generators running. What does it do? It should start cutting loads off, because it is going to inherently protect the system. I mean, that's the final goal, is to protect the priority 1 loads and make sure their life safety loads stay on. Another feature to test is the generator demand mode. You want to make sure that if you're trying to save fuel, so if you have a long 7-day outage, you want to make sure that your generators, if they're not necessary and they're not even close to necessary from like a startup of a chiller, then you shut one off, and it does it automatically. And then if the load closes up to maybe 80% of one engine, maybe then at that point you decide to bring on the 2nd engine. And those values are typically adjustable, or something that you could specify, and then in the field test it out and check it to work. All this is done with the PLC milliamp generators or PLC inputs and stuff like that. Another feature to check out in the field is bus under frequency. It's important to know that the feature exists, because if the generator systems see a bus under frequency, they will drop all non-priority 1, non-life safety emergency loads, drop them all, and it will lock it out. So that means in the middle of the night, somebody has to go there and unlock it out to figure out what happened. The thought behind under frequency is that it is catastrophic at that point, and typically there's like a 3-second delay for under frequency, and you can see it lock everything out. So in the field, it basically would be a little jumper, and you jumper across the under frequency. You watch all the switches shed, except for your priority 1, and know that this will work the way it's supposed to. You also want to look at your e-stops. Typically, most AHJs and the code requires e-stops outside of the building or outside of the generator room, I should say, and they're meant to turn off the engines. There's an event. Some building types you require remote ATS controls, such as a high-rise. So you will have to also check that as well. So just to kind of run through all of the plethora of information that we covered, we talked about the codes, and here are some of the major codes. We talked about system capacity and how to use the systems. And then we talked about selecting the system and the fuel sources, whether or not redundancy, what the redundancy requirements are, where we put it. And then we finished with installation and commissioning. Talked about load banks, annunciation testing, system switchgear testing. I hope that everyone enjoyed the webcast, and look forward to the questions. Back to you, Jack.
Rob, Jim, thanks so much for a terrific presentation. As our presenters are preparing for the Q&A session, on your screen is a list of code references from today's presentation. Rob and Jim will take your questions now from the audience, and type your questions for today's presenters in the Ask a Question box on your screen. Please indicate which speaker you would like to answer your question by typing his name before the question. If you're on Twitter, you can tweet your questions to us by using hashtag CSEGenerators. We will get to as many questions as we can, and the questions will be answered verbally during this Q&A session. Within a few days, this presentation, including the Q&A session, will be available for on-demand viewing, and we'll send you an email when it's ready. You can also access the webcast from the Consulting Specifying Engineer homepage at www.csemag.com. Okay, Rob, the first question will go to you. When and why is it appropriate to set up a separately derived system? And maybe elaborate a little bit on what the criteria is for separately derived system.
Okay. Typically when I design a system, they're all separately derived. But a couple things to think about if you're thinking about a non-separately derived system is GFP. If you're 277, 480 volt utility coming in, the non-separately derived system could end up tripping the upstream GFP on the utility. Also, let's see. If it's a healthcare facility, you have multiple levels of GFP, so it would have to be separately derived in that case for the GFP to operate properly. Maybe for a very small system, maybe 100 kW, or a Delta connected system, you could go non-separately derived, but in most other cases, I think it would need to be separately derived. When it is separately derived, you need to make sure your ATS has 4 poles, and that you're switching the neutral along with it, and you need to have grounding at your generator as well. Hope that answers the question.
And thanks, Rob. Jim, next question's for you. How do you handle wet stacking when you're doing load bank testing and or exercising?
Well, typically wet stacking is the term used for if you're operating your generators and they're running at less than 30% of the load, you may cause wet stacking. It's kind of, if you're wet stacking, then you need to use a load bank in your tests in order to make sure you're not wet stacking and bring your load up above 30. You don't necessarily, that load bank is not the size of 30% of your engine. It's just the amount you need to get above 30%. So if you're running your load and you're probably at 28%, you don't need a huge load bank, but you would need a small load bank in order to bring you up above 30%.
Thanks, Jim. Rob, can you shed legally required systems?
It's not something you want to do, but the code actually requires it in 700.4b in the NEC. Basically, if you don't size your, basically the code requires you to size your generator based on all of the connected loads on the emergency system, but it allows you to account for all of the loads that are intended to operate at the same time on the legally required system. So basically what the code says is if you do that, you need to have selective load pickup and shedding, and it needs to go in the order of 1 emergency circuits, 2 legally required standby, and 3 optional standby circuits. If you size your generator based on all of the connected loads for both systems, I believe you don't need the selective load pickup, but a lot of times to keep costs down, you're not accounting for every connected load if you know they won't operate at the same time.
Jim, is there anything you'd like to add to that?
No, I think that's appropriate.
Then I'll give you another question, Jim. On the engine ratings, the term limited time power, LTP, could you explain that?
LTP would be for all of the generator ratings, you need to be mindful that there's a couple of ratings in NFPA 110, but like limited time power is not in NFPA 110. There are different definitions by manufacturer of some of these criteria, and some of the different ratings. They do use some different ratings, so you need to be familiar with what each manufacturer offers as well, which would be limited time power.
Thanks. Rob, here's a long question for you to describe the proper percentage load that is best for a diesel generator over an extended period based on your suggested method of conservation of standby, prime, and continuous ratings. In other words, does specifying prime rating versus standby rating increase the longevity of the generator?
I think I might pass this one to Jim if you could.
Sure. So the rating of the generator, you would certainly get a more robust generator if you're calling for a continuous rated generator than a standby rated generator. But if you're, let's say you want a 1500 kW generator, at standby it's going to be X size, and at continuous it's actually a bigger generator at a bigger size. That continuous generator that you're calling for 1500 kW would actually be equivalent to, let's just say 1800 kW standby. So you are getting a little bit more robust unit, but you are also getting the space and paying the money for it.
Thanks, Jim. Rob, can the ATS be in the same room as the generator?
Yes. NFPA 110 allows the ATS, which is part of the EPSS, to be located in the same room as the EPS, the generator. I think earlier in the slides we had a code reference for that. I'd have to...
And that would also apply to the parallel switchgear.
Correct.
Jim, here's a question for you. clarification regarding load bank testing. Reactive is 0.8 and resistive is 1.0 power factor?
Yes, that's correct. That's correct.
Rob, do any of the codes mention special emergency power requirements for storm shelters?
Let's see. Do you know, Jim? Do you have a?
I would think that the NEC Article 700 is critical operation power systems. Typically, that would be something that's classified as critical operation power systems, but I think if you're using a storm shelter, that would probably fall under that criteria. So a lot of these things that we talk about would apply to a storm shelter. If it's like a public storm shelter, it may apply to that.
And there again, the AHJ would probably have the say on that?
Yeah, I would probably reach out to your AHJ to figure out whether or not it was a considered necessary for the health and safety of the community or something like that.
Jim, in one of your slides you mentioned normal loads for one of the ATSs. Aren't all ATS loads by nature considered emergency loads?
No. I would say probably the right term I should use would be non-essential. Non-essential would be, in a hospital you have the normal branch, and once it hooks up to an ATS, then it's really a non-essential branch. So, I use them equivalently.
Okay, we have time for probably one more question. Rob, I'm going to give this one to you. One of our viewers would like a little bit of extra explanation about the difference between prime and continuous.
I think that was on my slides, actually.
Oh, okay.
The continuous is, I have a 1500 kW generator, and I'm running 24/7, absolutely 24/7 at that rating, and it's available all the time. It's basically I would be running off of that as my primary source almost. Prime power, the load does vary a little bit, and the derating of the generator is not as much typically. So it would vary a little bit on that load for prime power.
Okay, Rob, how about this one? If you are relocating an existing generator from one campus to another, is NFPA 110 reactive load test required, or can resistive be used?
I think that was a Jim slide as well. I'm sorry.
That's a good question. I would say if it's a newer generator and you have a copy of the reactive load bank test, then that's something you can certainly point to, and there are some provisions in NFPA 110 for kind of redoing your load bank tests and what the criteria are for it, so you could follow that. If you don't have it, then I would certainly require a reactive load bank test for that new installation.
I'd like to close by thanking our terrific speakers, Rob Jones and Jim Ferris, for generously sharing the time and expertise for this webcast. A lot of good information here. I'd also like to extend special thanks to our sponsor, ASCO, for supporting today's event. Please take a moment to check out other consulting specifying engineer webcasts